So we'll try to finish that. ఏదన్నా కానీ 12 మంది 13 మంది 11 మంది 10 మంది క్లాస్కి అటెండ్ అయితే మా క్లాస్ చెప్పాలనే ఇంట్రెస్ట్ ఎక్కడి నుంచి వస్తుంది నాకు అర్థం కాదు. సో అందుకని ఇంకా మేము కూడా టైం పాస్ చేస్తాం, ఏం చేస్తాం. Okay, so I think most of you already noted down this problem in the previous class. So now we'll see the solution for this. So in the previous classes we already discussed how to design an helical spring which is subjected to axial load. So in the discussion, if you recall it, so we said that there are three important parameters in any spring design. These are wire diameter, mean coil diameter, and then number of active turns. If you are able to calculate those three first, then remaining things are you can calculate it from those three parameters. So that's why here, if you look at this particular problem also here, he said that design the spring and calculate first wire diameter, 2 mean coil diameter, and third one is number of active coils. The first 3 points are only going to be those three. So now to find out these diameters, the requirement is first you should know what is the load acting on the spring, what is the maximum load on the spring, and also at the same time you should know what is the maximum compression or elongation in the spring. We can call it as maximum deflection in the spring. So for any design problem on the spring or especially on helical springs, the first step in the design procedure what we already discussed is you should know what is P, what is delta, or P and K. Either way it is okay. So without those two things you cannot design any spring. First thing is you need to look at into the problem whether that maximum load and deflection is given or not. Once maximum load and deflection are given or identified, then you can use the stress equations to determine what is the diameter of the wire as well as mean coil diameter. Then you can use the deflection equation to determine the number of active coils. So now if you look at this problem data, he has given the maximum force directly. So therefore that is P is available for us. P is given as 1250 newtons, and also has given that maximum deflection is delta is 30 mm. So these are the two requirements for any helical spring design. So he has already given those two values. P is 1250 and delta is 30 mm. In addition to that, he has given spring index C as 6 also. So that means he has given the relation between small d and capital D. So that means once I know the small d value, I can compute the capital D or vice versa. So then for the mean number of active coils, you need to use your deflection equation. For that you require delta. Delta is also given. Then it's over. So that means first we'll use the stress equation to find out or to determine the wire diameter. Then we'll use deflection equation to determine the number of active coils. After that, calculation of total number of coils. This depends upon what type of ends you are choosing for the spring. So depending upon that, you need to identify what are the number of inactive coils. Then your number of active coils plus inactive coils is going to be the total number of coils. Then your free length of the spring will depend upon this total number of coils, and then mean coil diameter and also the delta. Then pitch of the coil also. Pitch of the coil will depend upon the free length of the spring and number of coils. So that's it. So that means the main important thing is you need to calculate what is wire diameter, mean coil diameter, and number of active coils. Okay. So like I already said, for wire diameter we need to use the stress equation. So I'll take you through that. So now coming to the solution, this is the data what he has given. P is 1250 kilonewtons, delta is 30 mm, C is 6, SUT. So that is also given in the problem. So sometimes it may not be given. If it is not mentioned in the problem, you need to pick that from the data book. So here the ultimate tensile strength of the spring material is 1090 Newton per mm square, and the modulus of rigidity is nothing but shear modulus. He has given it as 81370 Newton per mm square. So this is G value, this is SUT value. So SUT given as 1090. So that's what I written here. SUT is 1090. So and similarly G is given, and even this is also given in the problem. See, you can see that the permissible shear stress for the spring wire should be taken as 50% of ultimate tensile strength. That means the allowable shear stress tau in the spring is equal to 50% means it is nothing but 0.5 only, 0.5 times SUD. So that's what I written here in the data. Okay, so once I list out the given data from the problem, we need to look at it whether this P, delta and C information on these three are available or not. So if they are available, so then you can calculate this allowable shear stress and then you can use the stress equations to determine what is the wire diameter. So that's why the first step is we need to determine what is the wire diameter. So for that, the permissible shear stress is already given, tau is equal to 0.5 SUT. So I substitute that SUT value in this so that I'll get the permissible shear stress, which comes out as 545 Newton per mm square. So SUT given as 1090, half of 1090 is nothing but 545. Then in order to calculate this wire diameter, so here the load is static load, so I need to use this wall stress correction factor to include both direct shear as well as curvature effect. So this is the formula for K, that is the stress correction factor. So which is given as 4C minus 1 by 4C minus 4 plus 0.615 by C. C is given as 6 here. If I substitute for C is equal to 6 and if I evaluate, I got it as 1.25. Then once you have a K value, then use the formula for resultant shear stress in the spring. So the formula is K into 80 PC divided by pi d square. Why I use C here? Because I know the C value, or else you might have seen the other formula also. You can say same tau is equal to K into 8 PD divided by pi d cube. So you can use this formula also. But the thing is, why I have written this one in terms of C? Because I don't know what is capital D, what is small d. Both are unknowns for me. In the problem data, I have C. Even though I have a C value, I don't know what is capital D, what is small d. So with one equation, I cannot solve for the two unknowns. Therefore, using the relation between this D and D, capital D and small d, which is nothing but our C. C is equal to capital D by small d. So then I eliminated one thing, that is I eliminated capital D. So by writing it as your capital D is nothing but CD, capital C into D. So now if I substitute in place of C, C into D, here this D cube and D will cancel out, it become 8 PC by pi d square. So accordingly we'll use like this the formula. Maybe sometimes instead of giving the C value, suppose if he has given capital D, then we'll use this formula. So that is depending upon the given data in the problem, we'll make a choice of this formula whether in terms of C or in terms of this capital D. Okay. So for this particular problem, since he has given the C, I'll write the formula for tau in terms of C only. So this is the formula. So in that, tau is the allowable shear stress computed as 545. I substituted for that 545. And remaining things is except the small d, everything is given in the problem. I'll substitute all those values. P is 1250, C is 6, so then phi is as is 5. So now if you take this equation, in this equation only D is unknown. If you solve this equation, you will get the D, which is nothing but your wire diameter. So if you solve that equation or if you calculate those simplify those equations, we'll get D as 6.63 mm. Maybe that is rounded up to 7 mm. So we got the first parameter, that is wire diameter. Then we need to compute the mean coil diameter. So mean coil diameter is again, like I said, we'll use the relation between wire diameter and mean coil diameter. That is mean coil diameter is C into D. So we know C value, which is 6, D is 7. Just now we computed. So you got it as 6 into 7 as 42 mm. So that is the second parameter is over. Then third one is number of active coils. So this will use, we will determine the number of active coils using the deflection equations. So what is our deflection equation? Delta is equal to 8 PD cube n by GD power 4. Now I know this capital D value. So then I can use capital D, or if I want to write this one in terms of C capital C also, I can write. Either way I can use the formula, it doesn't matter, because at this point of solution, we already know the C value, we know the D value, capital D as well as small d. It doesn't matter in whichever form you use that formula. So now this is the formula for our deflection, delta 8 PD cube n by GD power 4. So in that, we know delta, we know P, we know D, we know capital G, we know small d also. Only unknown is n. So now I can solve for the number of active coils, which is denoted by n. Delta is given as 30 in the problem, and then P is 1250, and capital D just now we determined it as 42 mm, and of course a capital N is unknown. Shear modulus G is given as 81370 Newton per mm square, and wire diameter we computed as 7 mm. So now if you substitute all the data and if you simplify this, from this you will get your number of active coils n. So if you calculate, it comes out as 7.91. But generally we don't have fraction coils, fraction number of coils. Generally we need to round it up to the next higher integer number. So therefore I will take the number of coils as active coils here. See, number of active coils, it should be 8. So that's it. So those are the three parameters. Once I know that, then what you ask is, what are the total number of coils? So total number of coils is nothing but number of active coils plus number of inactive coils. Like I already told, it depends upon what type of end styles you are choosing for your spring. So in this problem, he has assumed that spring has square and ground ends. So then the number of inactive coils is 2. For a square and ground ends, the number of inactive coils is 2. Suppose if you choose instead of square and ground ends, if you choose plane ends, then number of inactive coils is 0. So like that. So this is the designer choice. So that means you can choose any type of end for the spring. Suppose particularly in the problem, if we mention that the spring ends are like this, then you have to choose only that. Otherwise, you can choose any style of out of those 4 styles of ends, you can choose any one. So in this problem, you are choosing it as square and ground ends. Therefore, number of inactive coils is 2. The number of active coils is 8. Inactive coils is 2. Therefore, your total number of coils is 10. Inactive coils, active coils plus inactive coils, they comes out as 10. Once you find out this one, then we need to compute what is the free length of the spring. So for the free length of the spring, you should know what is solid length, what is the compression length, and also what should be the clash alliance. So you need to find out those 3 parameters. Once you've done that, it is going to be over. So for that, first to find out the clash alliance or deflection, maximum compression in the spring, delta. So even though he has given delta as 30, what he mentioned in the problem is it is approximately 30. It's not exactly 30. So if you go back to the problem data again, you can see here it is approximately 30. It is not the exact value. So now we decided the parameters of the spring. That means we calculated what is small d, what is capital D, what is number of active coils also. Now using the data, we'll compute what is the actual deflection in the spring. So we'll use again the same formula, but only thing is now we'll substitute what is the active. See, if I use this formula, I got it as number of active coils is 7.91. So when number of active coils is 7.91, then it is reflection is 30. But I rounded it up to 80. So 8 coils. So when the number of coils 8 becomes, this delta is going to change. So now I'm computing what is the delta here. So if I substitute as n is equal to 8, the deflection comes out as 30.34 mm. So we need to use this delta to find out the free length of the spring. That's why we are computing here that one. So then solid length, we know the formula, number of turns into total number of turns into wire diameter. So number of turns is 10, wire diameter is 7, so it comes out as 70 mm. Then it is assumed that there will be a gap of 1 mm between 2 consecutive coils when spring is subjected to a maximum force. So therefore total number of coils is 10. So here this is what I am saying about the gap or clash alliance. So in this problem, he has not mentioned anything about what is the criteria you need to follow to pick up that clash alliance. So therefore, we'll choose the gap between the adjacent coils as 1 mm. Since you have 10 number of coils, so therefore there are 9 such number of pairs of adjacent coils. 9 into 1 is going to be the total axial gap. So that's what he has calculated here. The total axial gap is 9 mm. Then free length should be solid length plus total axial gap plus delta. So now we computed all these three. Our solid length is 70, total axial gap is 9 mm, and delta computed as 30.34. So now if you sum up all those things, it comes out as 109.34. Maybe it is rounded up to 110 mm. So therefore, this 110 mm is going to be the free length of the spring. Once you know the free length, okay, I'll finish in 1 minute. Last one is pitch of the coil. So the formula for that is free length by total number of coils minus 1. So it is comes out as 12.15 mm. So like this, you can solve this problem. So only thing is, it is all these formulas, don't need to remember all these things also. All these formulas are available in the data book. The only thing is, you need to pick the data in from the problem and you need to apply those formulas. That is the only thing you need to do. Okay, so if you have any doubts, already 10:15 it is now. So if you have any doubt now, we'll discuss our doubts in the next class. You keep, or else you can post it in the Google Classroom. So నువ్వు నెక్స్ట్ క్లాస్ కల్లా నేను మర్చిపోతాను అనుకుంటే గూగుల్ క్లాస్లో చాట్ బాక్స్లో పోస్ట్ చేయండి. I will answer your doubts in the next class. Okay, so I'll stop the class now. Maybe in the next class we'll take up some more problems on this design of helical springs.